Alright guys, so the second part of this chapter we'll talk about is electric current and Ohm's law. Ohm's law will be like the really last slide we'll talk about. It's a really quick one, but electric current will take up most of what we'll talk about today. When we talk about electric current, okay, we talk about how many electrons actually move past a position in a wire in a given amount of time. So basically like a rate at which they actually occur. And how we'll measure electric current is by what we'll call amperes or amps. And amps are actually related to coulombs like we talked about last section, which 1 ampere is 1 coulomb per second. So that means, if you remember, 1 coulomb is 6.24, I think I remember correctly, times 10 to the 18th electrons. So that means in 1 ampere, I have this many electrons moving per second. But in order for electric current to actually happen, you have to have a complete path, okay? And most of you experience it sometimes like in some of your A classes maybe too. If you guys took, there's a class in middle school that talked about current also, where you have to complete a path in order for charge to flow, right? And a good example how you guys see that actually too is like in a flashlight, okay? When you put batteries in a flashlight, okay, they must be placed in the correct way so that charge can flow from negative to positive. So if you look at when you put batteries in this place, the charge flows from negative to positive, and that's what makes the actual flashlight actually light. Okay. While if you put them the other way, there would no be charge flowing, okay, because there wouldn't be in the correct position, so you wouldn't actually get the flashlight to work. All right. But another example of electric current, okay, is that even though electrons flow, okay, current is defined as the direction in which positive charges would flow towards the negative charges, okay? What I mean by that is if you look at this battery hooked up to a light, it's a really simple version of it, okay? Here's your positive, here's your negative, okay? We're talking about the flow of electrons actually goes from a positive side to the negative side. So the flow of electrons actually occurs that way. But the direction of the current is always the exact opposite of flow of electrons. So my direction of my current always essentially goes towards my negative. Okay? So your electrons basically will always flow from positive to the negative side of things. Okay? But when I talk about current, it's the exact opposite. So I'm talking about the flow from negative to positive then. Okay? So it's important to understand the difference between when I'm talking about the flow of electrons or the currents. So when we talk about this electric flow too, okay, we'll also have things called conductors and insulators that are related to that electric current. First thing we'll talk about is electrical conductors, which you've all have heard at one point. But this is material in which charge can flow through easily, right? So you have charge being conducted through it. Good example, these are like any metals, like copper and silver. Those are all conductors of electrical current because they can carry the current through things. While the exact opposite of a conductor is going to be an insulator, that's just material that which charge cannot flow easily through. That doesn't mean there is no charge at all. That just means the charge cannot flow as easily now. Okay, that's the biggest point to understand. There might be some residual charge flowing through, but not as much as conductors. Some examples are like basically your woods, your plastics, your rubber. Air is an insulator of things too. Okay. But this is why we always coat metal wires with insulators. Okay. Because if you didn't coat these metal wires with insulators, you would step on it and you would feel that electric charge and you would basically get shocked yourself. Okay. But this is why we have insulators on every single wire that we always used. But what allows metals to be conductors is because of metals, made of are made of ions, they're in this lattice form. Okay, and this lattice form is what allows the electrons to move freely around and conduct that electric charge, compared to insulators. And how that lattice actually looks is sort of like this. Okay, which if you look at this metal, okay, these black dots, these guys, these are electrons, while these ones, these are basically positive ions. Which in the metal, you can see that these electrons, these guys can basically move wherever they want in between these spaces, in between the positive ions, okay? While in non-metal, there are no ions, there are no electrons, right? It's just stationary, right? This movement is what allows them to be conductors, okay? And allow them to carry the electric current. While in non-metals, they don't have that ability to have the electrons move freely. They're all stuck, okay? While these guys can move which direction they want, and they're able to carry that electric current now, actually. But when we also talk about current, we also can talk about resistance. Okay, which resistance is the opposition to the flow of charges. Okay. And what I mean by that is as electrons move through a wire, okay, they collide with different ions in there. Which when they collide with those ions, it converts kinetic energy into thermal energy and thus reduces the actual material's current. Okay, so when electrons move through there, if they collide with things, it will reduce the current and thus create resistance. And we measure this in ohms. Which if you look at these two cases, we look at case A over here and we look at case B. We have a battery hooked up to a light. We're measuring the resistance of this current flow. We measure it actually as 3 ohms. Okay, which you can tell that means the resistance is pretty low. Electrons are actually moving freely. They're not colliding with ions in this case as much. But in situation B, my ohms is higher, my resistance is higher, which now means these electrons are colliding more with ions and reducing the current now. Okay, which means then this bulb will not shine as bright, which you can see. So the higher the resistance I have, the less current I have, and basically the lesser something will actually work, right? You see this case, the bulb won't work as much or as best as it does over here because there is more resistance in this case. Now there are also 3 things that we use to determine resistance. Thickness is the first one, okay? Which the thicker something is, the more easily electrons will flow through that wire, okay? Because there is less resistance. Okay, if you look at A and B again here, okay? B is a thicker wire, okay? The blue guys, all these blue ones are electrons, and these guys are what they're going to collide with. Which if you have a thicker wire, the electrons will be able to move more freely through this wire and not collide as much with these ions. While in A, you have a thinner wire, okay, the electrons are more likely now to actually hit these ions and thus create lower resistance. Yeah, a little higher resistance now. Okay. So in this one, you have a lower resistance R, and this one you have a higher resistance R. The next thing that determines resistance is length of the wire. Okay. When you look at this, resistance is greater in a longer wire because the charge has to travel faster. Right? Which it just makes more sense because if you have a longer wire compared to a short wire, there's more opportunities for the electrons to actually collide with things and then dissipate the current. While if it's in a short wire, there's not as much chance for it to collide with things, which means the resistance will actually be lower. So in a shorter wire, resistance will be lower, while in a longer wire, resistance will be higher because it has more chances to actually collide with those ions and create less current. And then lastly is temperature. Okay. How temperature affects resistances is as the temperature increases, a metal's resistance increases because they're just colliding more often, right? If you guys remember temperature, right? It's just the average kinetic energy of molecules, which if you add more heat to something, you increase the energy it has, which is moving faster. Okay? So if you're having things at a higher temperature, it's moving faster, it has more opportunity to interact with those ions, and thus creating a higher resistance. Which if you're at a lower temperature, it's not moving as fast, it probably won't collide with the ions as much, which makes it have a lower resistance. Okay? So the higher your temperature is, the more resistance you might have, because you'll collide more often with those ions. But next, real quick, we'll talk about voltage, okay? Which this is what we measure usually when we talk about like batteries. But this, in order for charge to flow, wire must be connected in a complete loop, like we mentioned before. So in this complete loop right over here, you see down below. That includes also a source of energy. So in this case, source of energy is a battery. Okay. So in this loop, electric charges always flow from a higher to a lower potential energy because they want to become lower. It's easier for them to become lower. It's like going down a hill. It's easier to roll something down a hill than it is to go up a hill. But this potential difference between the high and the low one is what we'll measure as voltage. Okay, that's the difference of potential energy between the two places in a field. So the highest part and the lowest part. And we measure voltage usually as either volts, which you see on batteries all the time, or joules per coulomb, which is a volt basically. Okay, but they mean the same thing. 1 volt is a joule per coulomb. So when we talk about voltage again, okay, the source of voltage actually works to increase the potential energy of electric charges. Okay. So the higher the voltage it has, the more potential energy it really has. And you see these all the time in batteries, solar cells, generators, okay? Because a battery converts what's going on inside is actually chemical energy into electrical energy. So that energy conversion stuff like we talked about last chapter. All right. And how we can actually use to measure usually like voltage or even current or resistance is called a multimeter, which I wish we were in class at this point because I would have you guys use these in class to actually measure current, voltage, or resistance, which if you're usually in a shop class, you'll use these a lot too, where you'll take the voltage of different things or the current or the resistance of things. But they are very, very handy. All right, lastly, before we end, we'll talk quickly about Ohm's law. Okay. And what Ohm's law does is he relates the voltage in a current, uh, to have a circuit, I'm sorry, to the current and the resistance. So what we'll call that is the voltage, V, is equal to the product of a current, which is I, times the resistance. So this is what Ohm's law states, is that voltage is equal to the current times the resistance. Which if you look at this, if you increase the voltage, you will actually also increase the current. When you keep the voltage the same, you keeping the same voltage and increasing the resistance decreases the current. So if you look at this, they're actually an inverse relationship. Okay, if I keep my current the same, but my voltage goes up, that means resistance has to go up in a sense. Okay, but this is the relationship that you'll look at essentially in Ohm's law, is that voltage is equal to the product of the current and the resistance. Okay, that's what he basically used. Right. But that's pretty much it though with Ohm's law and electric circuits. So you also have a homework attached to this, which will talk some about explaining things and using this equation. So make sure you know how to use it when it's voltage equals the current times the resistance.